Hey there, and welcome. Today, we're going to pull back the curtain on something you use literally every single day, but probably never think twice about, that invisible language that lets all your gadgets talk to each other. Let's jump right in.
Think about it, right? It feels like magic. You hit print, and somehow a piece of paper starts coming out of a machine all the way across the room. You save a file, and poof, it's on a different computer. Well, it's not magic. It's all thanks to the power of a local network.
And these networks, they're not just for convenience. They are the absolute bedrock of our modern lives. They're behind how we learn with online classes and digital collaboration. They're how we work, letting us connect remotely and share files in an instant. And of course, they're how we connect with friends and family every single day.
Okay, so here's the game plan for today. We'll start with why this stuff even matters. Then we're going to zoom in to the local area network, or LAN. After that, we'll meet the star of the show, Ethernet. We'll look at the blueprint it follows, and finally, we'll get our hands dirty with the actual cables and light that make it all real.
All right, first things first. We're not talking about the entire global internet today. Nope. Our focus is going to be on something much, much closer to home.
We're diving into the local area network, or what you'll usually hear called a LAN. And the definition here really nails it. It's just a group of connected devices that are all managed together, usually in a small area. So think of your home Wi-Fi network, your office, or maybe a school campus.
So what are the moving parts inside a LAN? Well, as you can see here, you've got your endpoint devices. That's the stuff we actually use, like laptops and printers. But then you have the really important gear, the infrastructure devices. The LAN switch here is kind of like a super efficient traffic cop for your local data, making sure every message goes to exactly the right device. And then you've got the router. Think of it as the gateway, the front door connecting your entire local network to the great big world of the internet.
Okay, so if all these devices are the actors on a stage, what's the script they're all reading from to make sure they can communicate? Well, for pretty much every wired local network on the planet, that script is called Ethernet.
And this quote from our source material really gets to the heart of it. Ethernet isn't just one thing. It's a whole family of technologies. And to really get how it works, we've got to look at the official rulebook for networks, which is known as the OSI reference model.
So what is this OSI model? Well, you can think of it like a universal translator for computers. It breaks down the super complex job of sending data into 7 distinct layers. And because of this layered approach, a device from one company can talk perfectly to a device from a totally different company. It's the reason everything just works. For Ethernet, we really only need to care about the bottom 2 layers.
At the very bottom, you've got the physical layer. This is the nitty-gritty stuff, the actual electrical pulses or flashes of light representing ones and zeros flying down a cable. Then, one step up, you have the data link layer. This layer is like the postal service of the network. It takes all those raw bits, wraps them up neatly into packages called frames, and makes sure each frame gets delivered to the right address on the local network.
All right, so we know the data is packaged into these things called frames. But when a computer sends one out, who's the intended recipient? Is it talking to just one other device? Is it yelling out to everyone? Or is it for a specific group? Ethernet actually has a way to handle all 3 scenarios. Let's check them out.
Well, most of the time, it's using something called unicast. As this diagram shows, it's a simple one-to-one conversation. The source device sends a packet, and it's addressed to a single destination. It's just like sending a text message to one specific friend. Private, direct, and super efficient. But then you've got the total opposite, broadcast. This is a one-to-all message. This is like getting on the office intercom and making an announcement. Every single device on the network gets the message and has to process it, whether it was meant for them or not.
And sitting right in the middle is multicast, which is pretty clever. It's a one-to-many approach. A single packet gets sent out, but it's only delivered to a specific group of devices that have basically raised their hand and said, hey, I'm interested in this. This is perfect for something like streaming a live video just to a specific group of subscribers.
Okay, so we've talked about the rules of communication, the what and the how. But what about the where? Where does this data actually travel? Now we're getting into the real, tangible stuff, the cables that form the very foundation of that physical layer we talked about.
And here's the key thing to remember. All this data, it's really just a signal, and every signal needs a path to travel on. We call that path a transmission medium. It could be a copper cable, a glass fiber optic cable, and yeah, for Wi-Fi, that medium is literally the air all around us. And this slide gives you a perfect side-by-side of the 2 main wired options. On the left is a coaxial cable, a type of copper wiring.
You can think of the data as electricity flowing through that metal wire. But on the right, you've got fiber optics, where data is literally teleported as flashes of light, zipping through a tiny, pure glass tube.
So, what's the real difference? Why pick one over the other? Well, copper's biggest selling point is that it's cheaper, but it has weaknesses. It can be disrupted by electrical noise, say from a big power line, and the signal gets weaker the farther it has to travel. Fiber, though? It's a completely different beast. Since it uses light, it's totally immune to electrical noise, and it can carry way more data over mind-bogglingly long distances. The catch? It costs more.
And this table here does a fantastic job of summing it all up for fiber optics. The advantages are huge: massive bandwidth, zero electrical interference, and very low attenuation, which is just a fancy way of saying the signal stays strong over long distances. On the flip side, it's more expensive, tricky to install, and that last point, unidirectional, just means light only travels one way down the tube. So for a two-way conversation, like browsing the web, you actually need two separate fiber strands working together.
Phew, okay. That was a deep dive, right? We covered a ton of ground, from abstract rules to physical cables. Let's take a breath and quickly recap the biggest takeaways from all of this.
So, if you remember anything from our chat today, make it these 4 points. First, LANs are those small, local networks in our homes and workplaces. Second, Ethernet is the king. It's the main technology running the show on those wired LANs. Third, the OSI model is the rulebook that tells Ethernet how to package data into frames. And finally, all of this data becomes a real signal traveling through a physical cable, whether it's copper or fiber.
You know, it's pretty amazing when you think about it. Every email, every video stream, every single thing you do online starts as a simple signal. So, the next time you hear that satisfying click when you plug in an Ethernet cable, just pause for a second. Think about that incredible, invisible, high-speed journey your data is about to take. Thanks for joining me.